Hello everyone, we are Team Phoenix Electric and this is the Annunciator, a continuation of a capstone project that initially started in the fall of 2020. Our technical directors include Sandro Silva, the Director of Engineering at Phoenix Electric Corporation and a URI graduate of 2002, along with Mike Smith, our Capstone Consulting Director and URI graduate of 2001. Our team consists of two engineers, myself, Nicholas Kostick, an electrical engineer on the left, and Daniel Wilkins, a computer engineer on the right. This project is sponsored by Phoenix Electric Corporation. I've included their mission statement here, which reads, to provide our customers in the electric power industry the customized solutions and technical services they require to meet their individual power needs. Phoenix Electric is one of the world's top suppliers of air-core reactors. They are also responsible for retrofitting over 50% of America's hydropower switchgear, as well as offering custom engineered solutions tailored to the needs of utilities. As it was one of my first questions upon entering this project, you might also be asking, what exactly is it that we are building? When an electrical process out in the field exists, how can you monitor the health of those signals? This is where the Annunciator comes in. By connecting up to 48 individual signals to the Annunciator, we can monitor such health signals. If something goes haywire and that process signal is lost, the Annunciator would immediately see this and trigger a fault for that specific channel. In addition, an audible alarm would enable, alerting nearby personnel immediate attention is required. The communication is transmitted to the LEDs on the Annunciator. The goal is to have this Annunciator a commercially available product sold in different configurations. There will be a 48, 36, 24, and 12 channel version of the Annunciator. To gear this product for commercial and industrial use, the Annunciator has been designed to be a rack mount device. There are many motivations for such a product to exist. Phoenix Electric believes there exists a gap in commercially available Annunciator products. By developing a first-party solution, this allows Phoenix Electric three major advantages. Decreased reliance on third-party manufacturers when providing custom services, full control of the vision of what an Annunciator should be, as well as expanding their market share in the power and control commercial space. For the Annunciator project, the goal is to present a functional prototype of the Annunciator system that would be functionally equivalent and reliable in comparison to current options available on the market at a significantly lower cost. This year's anticipated best outcome can be broken down into two categories. The electrical and hardware outcomes involve prototyping and fabricating a custom power converter that will power the Annunciator on a wide range of input voltages. Also, expanding flash memory capabilities to increase future reliability, provide updates to existing PCBs while expanding their functionality. Finally, to address RS-485 and fiber optic connections for external communication. The computer and software outcomes involve updating the graphical user interface, or GUI, to fit within modern industry standards. This includes a rewrite of the embedded code to focus on a clearly defined structure. Also, incorporating various predefined alarm sequences, enabling end-user configurability, and prototyping and implementing Modbus communication between the GUI and the Annunciator. All of these tasks have been accomplished, allowing us to achieve the best anticipated outcome. For the electrical and hardware outcomes, the primary goal was to replace the need for a commercial off-the-shelf power supply pictured here. Instead, an in-house and custom power supply was designed, shown on the right. By making this change, the Annunciator decreases its reliability on third-party manufacturers while saving cost. In addition, the already existing PCBs designed by previous year's teams were overhauled, adding features and quality of life changes. Their transformations can be seen here. I'll be getting into the details of the changes made later in this presentation. For the computer and software outcomes, the GUI was reimagined to fit within modern industry standards. The new GUI can be seen on the left compared to the old one on the right. To accomplish this, much of the existing functionality was changed behind the scenes, while incorporating the capability to scale with future hardware improvements. As a team, we had many accomplishments this year to achieve the ABO. For the electrical and hardware side, the panel's LED's brightness has been optimized via power requirements analysis. Power converter components have been researched and selected, which were then prototyped on a breadboard. The resulting configuration was transferred over to a fabricated PCB that was built and tested. Internal memory was upgraded. The panel contains a new USB human interface solution. These tasks were accomplished during the fall 2022 semester. For this semester, the main and display PCBs were overhauled, simplifying them and adding functionality. Full bill of materials documents were generated for each of the individual boards, and all boards have been fully tested and verified to be working as expected. On the software and computer side, the GUI was rewritten using a strongly structured programming style, object-oriented programming. Added a virtualized annunciator for the GUI, which allows the user to visually work with the physical model. The embedded code was rewritten to take vastly less space, 93% down to 38% embedded memory usage. In addition, a new communication protocol was developed for the GUI to Arduino interaction. Finally, new alarm sequences were implemented. These tasks were accomplished during the fall 2022 semester. For this semester, the GUI was optimized and configured to allow for several new customizations, all that increase usability and efficiency. Finally, RS-485 and fiber optic communication protocols were implemented using the Modbus protocol. Working with Phoenix Electric Corporation, our team has created an in-house Annunciator solution that provides Annunciator panel options at lower costs, greater user configurability compared to existing products, and control over the hardware makeup of the product, guaranteeing quality and ethical responsibility. Shown here is the block diagram for the Annunciator system. Here, an Arduino is the heart and brains of the system. The Arduino provides power to the main board mounted ICs, including transceivers and memory, but it also acts as a communication bridge for the internal components. The power distribution system can be seen on the lower part of the screen in red. As shown here, the newly designed power converter takes an input of either 125 volts AC or 125 volts DC and outputs on two unique power rails. 5 volts DC to power the LEDs, and 9 volts DC to power the Arduino and the buzzer. Breadboard prototyping began with this converter after initial design considerations. Commercial off-the-shelf converters from reputable power electronics companies were selected to handle the conversion. With the future goal of getting this design UL certified, additional circuitry was added for immunity and emission requirements, as well as filtering. Many versions of this prototype were realized before this final one you see in front of you. To verify functionality, a 125 volt DC power supply was input to the circuit. As you can see, approximately 9 and 5 volt rails are output. After verifying functionality of the design, it was time to realize a more permanent solution, a PCB. The goal in the first version was to make the board as component dense as possible. This version was created before I had a solid idea on where exactly the board was to be mounted. Unfortunately, this is not realistic, as the board would be plagued with arcing and EMI issues. In version 2, component spacing considerations were priority. The AC and DC sides were completely separated. In addition, individual component spacing was significantly increased. This is the third and final. Its shape is a result of the location in the chassis it will be mounted. A slot was added to further separate the AC and DC sides of the board, and the input and output headers were finalized. In addition, the existing PCBs have been redesigned. Shown here is the display board. The purpose of this board is to house 12 LEDs each, and display their statuses based on the differential signals tied to them on the connector in the back. Each LED resistor has been modified to allow the LED to achieve optimal brightness. Instead of different resistor values for each color, one universal value was picked, reducing cost and material complexity. Part routing has been cleaned to allow for more efficient routes. and connector connections have been modified to allow for power distribution compatibility with the new converter. The main board was also heavily modified. The main board houses the Arduino and other important ICs that provide a wide range of functionality to the user. To start, a fourth push button was added to the bottom to allow user to silence the alarm, a feature prominent on many competing devices. The alarm buzzer design was changed from a chassis-mounted, plugged-in part to a board mount component. This reduced footprint and assembly labor. Many of the board's components were grouped and labeled to easily indicate what purpose they serve. A cutout was added to the top left of the board, which allows sufficient clearance for the newly implemented USB to panel connection solution. Finally, parts were reconfigured to accommodate cleaner and more efficient routing. Unfortunately, supply shortages due to COVID have greatly impacted the Annunciator project over the last 2 years. The current memory solution was selected during such time, which involves a voltage level shifter to operate. With supply making a comeback, this solution was reevaluated, and a new memory IC was selected that didn't have this requirement. I was able to double memory capacity while simultaneously reducing cost. This is accomplished by the removal of the level shifter and associated passive components. During our time working on the project, Sandro's team has been at work redesigning the Annunciator chassis based on our specifications. Pictured here is the new front panel. It features a new cutout for the USB interface cable and the additional push button previously discussed in the mainboard changes. The front panel has also been switched to more durable material and its color has been changed to black. The new rear panel shows the existing cutouts, but also features a new cutout for the newly designed power converter on the right-hand side. Shown here is the part breakdown of the Annunciator system. A complete 48-channel Annunciator features the following internal boards from left to right. The custom power converter, followed by 4 display boards, followed by the main board. All the boards are seated upright to allow for the LEDs to be correctly oriented. Here's the final product of the Annunciator system. As you can see, it is being powered by the newly designed power converter. It was tested here using 125 volts DC power supply, and it successfully powers the Annunciator. It was also tested using 120 volts AC with identical results. I would now like to introduce Daniel Wilkins, who will discuss the computer and software advancements made throughout this project.
As a computer engineer for Team Phoenix Electric Corporation, I worked on 3 facets of mostly software for the Annunciator cabinet. The first being a rewrite of microcontroller's embedded code for more reliability and function. We also added several new features. We also completely overhauled the graphical user interface. We greatly expanded its use case and made it much easier for the user to configure the Annunciator hardware. And the final task that I worked on this semester was implementing RS-485 and fiber testing with the Modbus communication protocol. So for the Arduino embedded code rewrite, we reworked the entire embedded code structure. We used memory saving techniques to reduce the size compared to the legacy code by 60%. We future-proofed it by making it much more accessible for future programmers to work on by using very rigid structures and coding techniques that will enable the work on it for future teams. And for new features, we added 3 new alarm sequences, the R129 and F2M1 alarm protocols. These utilized several new features such as ringback and first out alarm sequencing. We also made it so it connects to the GUI in a much more advanced way. It sends more data and also receives more data to the GUI. We also did better port monitoring and for the GUI so it connects to the correct port every time. And we also used log file management to label the actions on the Annunciator as they happen. And on the right here, you can see this is our flowchart of the Annunciator, all the connections that you might see. So the Arduino can connect to the GUI, which is also connected to the virtual Annunciator. You can see all the different components in there. And here is the GUI. You can see several of the upgraded features on here, such as the log viewing window and the port selection column. So for the log viewing window, you can see on the bottom right, in the red circle area, you can see that there's a way to view the cached log off of the Annunciator hardware, and you can also send a command to clear this as well, to prevent it from building up too much. You can also see there's an area to refresh the ports that are connected to the HMI, so that way you can select the correct port for your hardware. There is also the virtual Annunciator, which is the entire top portion as you see, which allows you to see the front panel of the Annunciator hardware on the GUI itself. Test the capabilities of Fiber and RS-485 with the Modbus communication protocol. We first proved the capabilities of communication through serial over both Fiber and RS-485. To communicate over Fiber, we utilized a breakout board which would allow our PC to connect to Fiber through micro USB. We did this by creating a relay on the Fiber boards, which would relay the signal from micro USB to Fiber, which would send it to the device. Then when it receives a response, it would send it back over micro USB to the HMI or computer that you're using. We also did this with a direct connector through Modbus. There was an adapter that we used, and we were able to prove that it was both capable of outputting serial to Fiber and RS-485. The next step for doing Modbus communication protocol was to test the actual capabilities of this. So we created a precedent for Modbus communication by proving its capabilities on both Fiber and RS-485. And we did this by sending and reading coils over Modbus. Me and Nick would like to extend our gratitude to the entire Capstone team, but especially to Dr. Harish Sunak for putting this program together. He really chose a great project for us and connected us in a way that really made us excel on this team. We'd also like to thank Sandra Sylvia for presenting this project to us from the company Phoenix Electric Corporation, and also providing great ideas and insight onto what to develop in this project. And also we would like to thank Mike Smith for his technical advice on this project. It really was able to enable us to create a much better outcome for both of us and Phoenix Electric Corporation. Thank you, everyone.